Last class, we talked about trigonometric functions. In this semester, trigonometric functions are going to be a very heavy topic. But prior for us to begin with trigonometric functions, we're going to round up with a very interesting topic on polynomials, the last thing of polynomials that we're going to go over. So this will give you some time for you to practice the trigonometric skills that if you don't have or you're missing them, like it is a great opportunity for you to practice them. Right now we're going to focus on this last thing of module 1 called the definition of parabola. So of a parabola. So in your previous algebra courses, a parabola was just like, okay, something like y equals x squared. That was a naive definition of a parabola. Parabolas are a geometric space in the same sense as a circle is a geometric space. What is the definition of a circle? Let us make a little space, a little parenthesis to talk about circles. So the definition of a circle is the set of points. OMG, what is happening? The definition of a circle is the set of all points that are equidistant from a point called the center. So a circle is the set of all points that are at the same distance from a fixed point. So all of the points in a circle are the points that are at the same distance from a fixed point called the center. So I want you to hear that definition. I want you to think of that definition. So that definition allows us to know if a certain point in the plane belongs or does not belong to the circle. So like, for example, let us think about the circle with center at the origin and with radius, I don't know, 2. So for example, the point 0, 2, it does belong to the circle because it is at a distance of 2 from the origin. The point 2, 0 also belongs to the circle because it is at a distance of 2 from the origin. Mr. Kachoa. The point what is it? So if this measures 2, it is a 45, 45, 90. So that is square root. Okay, Mr. Kachoa, you should have prepared this better. If this is x and this is x, so this is 2 over square root of 2, 2 over square root of 2. This point is also at a distance 2 from the origin. So I can think of all the points that are at a distance 2 from the origin. If I grab another point that is not at a distance 2 from the origin, I just need to calculate the distance and check that it is bigger than 2 or smaller than 2. So the definition of a circle, like all the points that are at the same distance from a fixed point called center, it is a definition of a geometric space. In the same sense, we can give a definition as a geometric space of a parabola. A parabola, okay, so in the circle we have the radius and we have the center. With those two elements we can define the circle. A parabola is the set of points. A parabola is the set of points that are equidistant to a fixed point called focus and to a line called directrix. So I've just like Googled how to pronounce this word. I like, as a non-native English speaker, I have like struggled with this word directrix. Directrix, I want to say directrix, but no, directrix. And in plural, directrices. So directrix. So in a parabola, I have 2 points. Well, I have 1 point that's very important and special called the focus. And I have a line called the directrix. And the distance from any point over the parabola to the focus is the same as the distance to the directrix. So grab another point, any point, a point here. So the distance from the point to the focus is the same as the distance from the point to the directrix. Grab any other point. For example, the vertex. That is a point that you already knew from Algebra 1. The distance from the focus to the vertex is the same as the distance from the vertex to the directrix. So we are giving a definition that is a way more formal definition than just the graph of something like this. A parabola is the set of points that are equidistant to a point and to a line. So if I go far away from the focus, so the distance from the focus to the points increases. Also the distance from the point to the line. This and this measure the same. Like the vertex is the closest point to the focus and to the directrix. Okay. The things that you already know from what we're gonna do right now is that we're gonna see how this definition and the previous definition that you already had from a parabola are the same. But prior of us going to that, it's gonna be a big problem because look how much space I left here, and then we're gonna be like suffocating. Like, okay. There is a property that makes parabolas super special. Like, if you have seen antennas or mirrors, like there is a very interesting property regarding parabolas that is called the reflective property. This property, we're not gonna prove it because to prove it, we're gonna need like more advanced math and more time and more energy. So we're only gonna mention it. So the thing with parabolas, why do we see parabolas all around like the world in antennas or in telescopes? It's because, or in glasses, it's because like if any ray that goes into the parabola that it's perpendicular to the directrix will reflect into the focus. Any ray that it's perpendicular to the directrix when hitting the parabola goes into the focus. Any ray that hits that it's perpendicular to the directrix when hitting the parabola reflects into the focus. Any ray that is perpendicular to the directrix reflects when hitting the parabola reflects to the focus. Any ray that it's perpendicular to the directrix when hitting the parabola reflects to the focus. So any ray perpendicular to the directrix, oh, did you heard? To the directrix reflects to the focus of the parabola. Okay, so what does it mean to be perpendicular? Like, for example, imagine like this ray. This ray is not perpendicular to the directrix. when this ray hits the parabola, like it can go anywhere. So this is an example of a non-perpendicular ray, and oh my god, sorry, and like this. So when a non-perpendicular ray, a non-perpendicular to the directrix ray hits the parabola, this ray reflects into any direction, like that one I don't care. But a ray that is perpendicular to the directrix, like for example, if I draw this ray, so this one is perpendicular to the directrix, and this ray is going to reflect to the focus. That is why it is parabolas are widely used in antennas and in glasses and telescopes, because in the focus is where the parabolas concentrate all those signals or those rays, all that information. That is why parabolas are very useful in that sense, no? Okay, so that was a little parenthesis, a little cultural parenthesis. So today's objective is to understand this definition. Like, if you're not understanding it right now, it's okay. It's okay. We're gonna understand it. Beautiful. So, first of all, why don't we try to draw a parabola? So my directrix is the x-axis and my focus is 0, 2. So I'm gonna draw at least 3 points because I think that I cannot draw more. This is not easy, kids. It is like when we were doing the drawings for the circle, it is not immediate. This shouldn't be as easy, especially it is harder, no? Okay, so I have my directrix and I have my focus. Which points are at the same distance? Well, one point that it's very clearly at the same distance is the midpoint in between, like the segment, the closest, the distance that joins the focus and the directrix. So that point is the vertex of my parabola. Great, because it is at a distance of 1 and at a distance from both the focus and from the directrix. Now, look that we can graph another point. So this is at a distance of 1. So like in a distance of 1, also from here and from here, like we are finding this distance. Now at a distance of 2, think of all the points that are at a distance of 2 from this point. In this circle, is any other point that is at a distance of 2 from the directrix? The answer is yes, there are 2 points. Like, look at the circle again. So, all the points at a distance, Mr. Cachoa, all the points at a distance of 2. Which, Mr. Cachoa, por Dios. All the points that are at a distance of 2 from this point. Which points are at a distance of 2 from the directrix? It's very clear that I have 2 points, one here and the other one here. So this is like a rough sketch of a parabola, like I am only drawing accurately those 3 points because another accurate point would be too far away. But yes, so this is the first thing that I wanted you to do, to draw it. Now we're gonna go for the hard thing of the day. So if you were able to find these 3 points, like where are these 3 points in the parabola? Because this distance is 2 and this distance is 2. This distance is the same as this distance and this distance is the same as this distance. So any other point, for example, this one is at a, no, Mr. Cachoa, this one should be, this distance should be the same distance from here to here. This distance should be the same distance from here to here. That is what my parabola does. Okay, so I know that at least it does it in these 3 points. Um, Now we're going to go for the tough part of the class. The tough part of the class is to find the analytic equation. So what does that mean? Oh my god, maybe I should have written down an equation here. To find the analytic equation, so the analytic equation arises from the distance from any point P to the directrix is the same as the distance from the point P to the focus. So a parabola is the set of points that satisfy this equation, the analytic equation. Okay, so any point in the plane, so I need to write down that expression. I need to write down the distance from a point to the directrix is the same as the distance from the point to the focus. What is the distance from any point to the directrix, the x-axis? Like, for example, if I have this point here, the negative 3, 4. What is the distance from, the 3, negative 3? What is the distance from this point to the directrix? Oh, well, it is just negative 3. What is the distance from the point negative 5, 4 to the directrix? Well, it is 4. What is the distance from, I don't know, this point, the 6, 6, to the directrix? Well, the distance to the directrix is 6. So the distance to the directrix, right now, we're only going to use horizontal directrices. So the distance from the point to the directrix analytically is just this. So if my point is x, y, so this is just y. Because if I have any point here, any point x, y, the distance from this point to the directrix is y. Great. Now, what is the distance from any point to the focus? The distance from a point to the focus, here we need the formula distance. The formula distance is x minus, my focus is at 0, 2, 0 squared plus y minus 2 squared. So remember that the formula distance, I'm just going to put it here. This appeared in the final exam. The formula distance is x minus x1 squared plus y minus y1 squared. No, it arises from the Pythagoras theorem. So here I have my my equation. This is my analytic equation. Y equals to the square root of x squared plus y minus 2 squared. So, what can I do now to manipulate this expression? Well, I could make it look nicer because here I have, okay, I don't like radicals, no? Like, radicals are ugly. This, if you give me this in your exam, because I am going to ask this in the exam, I'm going to ask you to draw one with at least 3 points because asking you for more points would be obscene. If you give me this, I am not giving you the full credit because you can do more manipulation. You can do more. You're Algebra 2 honors students. Like, try to find like the most beautiful expression that you can. But Mr. Cachoa, what is the most beautiful expression? How does the most beautiful expression look like? Oh, let me show you, please. So I don't like radicals. So I'm going to square both sides. So that is y squared equals x squared plus y minus 2 squared. Now I am going to foil this. I'm going to foil this. So that is y squared equals to x squared plus y squared minus 4y plus 4. And you know this, right? Because like I use the a squared plus 2ab plus b squared, or write this two parentheses and use the distributive property. This is why I wanted to get rid of the radical and to foil, because in this side I have a y squared and in this side I have a y squared. And by subtracting y squared on both sides, and I'm gonna solve for y, so I'm gonna add 4y. I am canceling the y's squared. This is x squared plus 4. So y equals x squared over 4 plus 1. This is the expression that I was looking for. Please, I want you to develop this sense of aesthetics. This is not as beautiful as this. Here I have a radical. Here I have a y squared. Like in this is beautiful. And this is like the normal definition of a parabola, no? Like what you have seen in algebra 1. This is like if you were like in algebra 1 and I asked you what type of graph would I get from doing this? Oh, it is a parabola. Oh, and what type of graph would I get from doing this? Oh, that is new. That is so crazy. Oh yeah, you're in algebra 2 honors. Now you know that all the points that are at the same distance from the directrix and the focus will give you a parabola. So yes, this is a hard thing to do. If you are a little bit scared, that is perfect. You should be. And you won't be in like 5 more minutes, because we're gonna practice this. So, for example, look at this graph. Here, I am giving you a parabola, and I am giving you already the focus and the directrix. So I know that the focus, and they are asking me for the analytic equation. So the focus is the point 0, 4. And the directrix is the line y equals to 2. So I need to write again my analytic equation. The distance from point P to the directrix is the same as the distance from point P to the focus. How? Okay, so let us investigate what is this, right? Because that was the hard part here. Like, what is the distance from a point to this directrix? So I have the directrix here. What is the distance from the point 1, 0 to this directrix? So the 1, 0 is at a distance of 2. Okay, what about the point -2, 4? The point -2, 4 is also at a distance of 2. So what is the distance, for example, from 0, 5? The distance from 0, 5 to the directrix is 3. How would you calculate the distance among a point and this line y equals 2? So I hope that you're noticing that the distance, so if I have a point here, the point, I'm going to draw it because I really want you to get it. I'm going to draw it. I'm going to draw it here. So I'm going to make it as a little square, like so. Here I'm going to put like how to find the distance from the point to the directrix. Well, so if I have a directrix of y comma k, of y equals to k, so the distance from my point P to the directrix, this distance this distance, if my point is x comma y, this distance is just basically y minus k. Independently, if I am over or under the line, the distance from the point to the horizontal directrix is just y minus k. So in this case, the distance from my point P, from any point P in the plane to this directrix is just y minus 2. And the distance formula, I'm also going to put it here, so in a little green square. So how to find the distance from the point to the focus. So if my point is x comma y and my focus is x1, y1, the distance is just the square root of x minus x1 squared plus y minus y1 squared. So this would be, in this case, the square root of x minus 0 squared plus y minus 4 squared. Okay, now you don't have the full marks for giving me this answer, but this is a beautiful answer. So I'm gonna square both sides. X squared plus y minus 4 squared. I'm gonna FOIL, so this is y squared minus 4y plus 4 equals to x squared plus y squared minus 16, minus 8y plus 16. Again, the y squareds cancel out, and I'm going to solve for y, so I'm going to add 8y, so I'm going to have 4y equal to x squared plus 12. Am I right? I think that I am right. And then y equals to x squared over 4 plus 3. So this is my analytic equation. Please look that we did the same as here. And this is what I am expecting you to be capable of doing. Of calculating the distance from the point, from any point, like an xy, to the directrix, that is explained here, to calculate the distance from any point xy to the focus, that is explained here, set them equal and solve for y. Those are the steps that you need to follow. Okay, now we're gonna go for harder problems. Okay, so now we're gonna go for harder problems. I hope that they fit in this schizophrenic amount of space. So I am giving you a point, the point x comma 4, and I want this point to be equidistant from another point and another line. So what is the distance from this point x comma 4 to the line y equals -1? So the distance from a point to a horizontal line, so this point is x comma 4. I don't know where this point is, but it's here. Here I have the point x comma 4. And here I have the line y equals -1. So what is the distance in between this point, wherever it is, to this line? Well, it is clearly 5. Because 4 is the distance from here to the x-axis, and 1 from the x-axis to the line y equals -1. That is the hard part, no? Right, so the distance from the point to the line is 5. Now, what is the distance from the point x comma 4 to the point 0 comma 1? Well, that is the square root of x minus 0 squared plus y minus 1. I'm Mr. Cachoa, 4 minus 1 squared. 4 minus 1 squared. So I'm gonna set these two things equal to each other. So 5 equals to the square root of x squared plus 3 squared. So 25 equals to x squared plus 9. So 16 equals to x squared. So 4 equals plus minus 4 equals to x. So these are the two possible values for x. And if you draw it, like, so here is the point 0, 1. So this point, the minus 4, sorry, the 4, and the minus 4, are going to be at a distance of 5, both from the focus as for the directrix. Now that is going to be 3 points in my parabola. Excellent. Okay, now this is a 3-step problem. The first one is very easy. So we're talking about the equation y equals x squared, and we want to find 3 points that satisfy that equation. So it's very clear that 3 points that satisfy this equation is 1, 1, 2, 4, and 3, 9. That's very easy. Now we're going to show that these 3 points, each of them, are equidistant to this point and to this line. So what is the distance? I'm thinking how to organize this so that it doesn't look that messy. I'm gonna put it here in green. What is the distance from the point 0, 1/4 to the point 1, 1? Well, that is the square root of 0 minus 1 squared plus 1/4 minus 1 squared. And that is nothing but the square root of 1 plus 3/4 squared, so that is 9/16. And 9/16 plus 1, that is 25/16. Am I right? Yes. So this is the square root of 25/16. So this is 5/4. And what is the distance from the point 1, 1 to the line y equals to -1/4? So to do this distance, we do just 1 minus minus 1/4. So that is 1 plus 1/4. So that is 5/4. Yes. So this one is because of the rule, no? Because of the rule, the distance from a point to a horizontal line is just this subtraction, no? So in general, it is y minus k, but here my y is 1 and my k is -1/4. So it is 1 minus k, 1 minus 1/4. Excellent. I'm just gonna do another one because I won't have space and I want to do the last one. Sorry. The other one is 2, 4, right? So what is the distance? What is the distance from point 0, 1/4 to the point 2, 4? Well, that is the square root of 0 minus 2 squared plus 1/4 minus 4 squared. So that is 4 plus 15/4. Am I right? I think so, because that is 6, yeah, 15/4 squared. And it's very easy to see that 14/4 4 plus 15/4, that is 31/4. No. 31, no, Mr. Cachoa, sorry. I need to square first. That is 4 plus 225 over 16, because I need to square first. Then I multiply this one by 16, I add, that is 289 over 4, and that is over 16, sorry, and that is 17 over 4 without the square root now. Beautiful. And now the distance from the point 2, 4 to the line y equals to negative 1/4, we do the same. We only take y minus, but instead of writing y, I write the y value, 4 minus 1/4, and that is very easily, you can check, that is 17/4. So do it for the other point. I won't do it because like my space is very limited, as probably it is yours, but be smart, better than me. Okay, now in the last problem, they are asking us to check, to find the analytic equation of a parabola with focus at 0, 1/4 and directrix negative 1/4. If you have noticed, like that is what the problem has been suggesting, no? Like, it is taking some points of this parabola, and then, so if this is the focus and this is the directrix, then it should be the same, no? The equation that I should get in this problem should be y equals x squared. So what we are concluding from this beautiful problem is that y equals x squared is a parabola with focus 0, 1/4 and directrix y equals negative 1/4. Okay, so we're gonna do it. In general, I want to find an analytic equation. So that is the distance from P to the focus is the same as, my gosh, as the distance from P to the directrix. Okay, so the distance from P to the focus, that is x minus 0, because 0, squared, plus y minus 1/4 squared. And the distance from P to the directrix is just y plus 1/4. I hope that you see why it's y plus 1/4. It is y minus 1/4. No, so it is y plus 1/4. Okay, I'm going to square both sides. So I have x squared plus y minus 1/4 squared equals y plus 1/4 squared. Then I'm going to FOIL, so that is x squared plus y squared plus, minus 1/2 of y plus a 16th equals to y squared plus 1/2 of y plus a 16th. This and this cancel out, this and this cancel out, so I have x squared. I'm going to subtract, I'm going to add 1/2, so that is x squared equals 1/2 plus 1/2 y. Beautiful. This is truly beautiful. Okay, so now your objective is to do this problem. So in this problem, I'm just going to guide you very quickly. So you just have to derive an analytic equation with this focus and the directrix being the x-axis, like y equals 0. This is the same as what we did, well, very similar to what we did in the first problem, no? In this problem. But my focus, instead of being 0, 2, now it is 0, negative 2. And now, how would I change that parabola into this parabola that I got here? What is the sequence of transformation? That is my example 1. This is the example 1, no? So how would you relate this parabola to the parabola that I'm going to get here?